During this section of the program, we're going to explore different causes of instability, such as over-maintaining a site, dredging it too deeply, straightening a stream out, and how do we start to accommodate some of the big depositional areas that you see in the background here. So let's get right into the section. When we talk about stream instability and some of the issues that we're trying to address in this program is that, streams, when we talk about stable streams, they've been evolving since the last glaciers about 10,000 years ago. And that's geologic time that streams have gone through all these different occurrences, these different climate patterns, these different precipitation patterns, and they've evolved a specific size, a specific width and depth and floodplain width. And there's been a whole bunch of activities that we've done over the last 200 years that have contributed quite a bit to stream instability that we now find ourselves needing to address. So really, how do streams become unstable? A lot of it has to do with our activities, so that when we respond to that excess sediment that's moving through a system, we may be engaged in dredging that may or may not leave the stream in better or worse condition due to some different development in the area. We might try and straighten a channel, berms which disconnect that stream from its floodplains, or any other ways that we disconnect floodplains from the channel will have an impact on that stream, and then development in that floodplain are just some of the things that we want to start to address. So, we can't talk about streams and sediment movement without at least touching on dredging. So as I mentioned, streams evolve over centuries to reflect the flow patterns that are in that watershed that Jeff talked about. And that typical stable pattern includes this uniform slope. So a slope to the stream will develop to reflect its valley and the area that it's dredging through. So if we come in here and we have excess gravel and we remove gravel below that uniform slope, the stream's going to respond somehow to fill in that hole. So what happens is that stream moves upstream and starts to grab bed load. It grabs material from the bed and banks of that stream and attempts to start to deposit that gravel to fill in that hole. And over time, it'll actually return to that uniform slope. Here's an example of someone's in there. For whatever reason, they thought there might have been excess gravel in there and they wanted to remove it. One of the first things that we see happen here that may not be such a good idea is they're taking that material out of the channel and depositing on the banks, which eliminates access to those floodplains. And if you eliminate access to the floodplains, you basically start to stack that water up higher, which increases the shear stress by confining that water and not allowing it to flow evenly into the floodplain. The other thing that we can kind of expect to happen is that this material was material that's bed load that was mobile to begin with. So basically, we're putting material that was mobile to start with on a bank, expecting it to stay there. And then when the next high flow comes along and that shear stress is even going to be higher than it was before, it's going to remobilize that material. And so we're going to see some consequences as a result of that. So here's an example of an area where, again, they just removed some material from the stream for whatever reason. They piled it up on the banks, again, eliminating access to the floodplains. They oversteepened an area, and if you look right here, it's oversteepened, and they flattened it out here. So, what's happening? We've got that steep riffle and that channel that's a little bit too wide. And so now we're going to see gravel deposition, even within the short time that this was excavated. And we're starting to see that erosion hitting upstream, where that stream is looking to grab that material, to take it out of the channel, to take it out of the banks and deposit it to fill that hole that we just left in the stream. And so we need to be aware of that process because there are unintended consequences to some of our activities, and that's what we're aimed at. So really, does dredging help flooding? Well, here's an example where some folks did some engineering, and that purple line is the original bottom of the stream. And what they did is they went in there and they theoretically dredged that stream 3 foot deeper to see if they could get more flow through that channel without engaging the floodplain. Well, when you look at the elevation difference in that floodplain before and after the dredging, it's hardly anything at all. So we're really not protecting our floodplains by dredging streams. So, how would you approach it? Well, here's a typical stream, and we can see here's a bankful elevation. And maybe I should clarify at this point what we're talking about when we talk about bankful elevations. Bankful is that elevation in the water flow in that channel that starts to mobilize that bed load material and starts to create the shape of that stream. So at that point, when we hit that flow at bank full, that stream starts to modify, evolve, or to show those some features that are a result of the deposition of all that material that's being moved at bankful. So when we disconnect the stream from bankful by making it too deep, we eliminate that access to floodplains, and floodplains act like a pressure relief valve. So when that pressure or that shear stress that Jeff talked about gets so high that it starts to rip and tear at the banks and starts to dig up that bed to that stream, it's able to dissipate its energy over a broad area of floodplain. So that floodplain is really critical to how that stream remains stable. So if we go in there and we, decide that, hey, we don't want so much flooding. We've got that 100-year floodplain out there. We've got bankful. Now we've just dug that stream a little bit deeper. We didn't really budge that 100-year floodplain at all. So rather, what we're proposing here is that you have a situation where you're disconnected from the floodplain. You have flooding issues. If we were to go in there and create a channel that reflects what that bankful, that shear stress that's stable, and the floodplain that's needed, we recreate that floodplain, we can significantly reduce the amount of flooding in developed areas. So again, by recreating that whole stable stream system, we can start to address that long-term stability of a stream channel. When we go to straighten a channel, just think about, what Jeff was talking about, that slope, that steepness. When you have a long meandering stream channel that goes from point A to point B, you have a long distance for that stream to drop out some of that power, some of that energy, some of that shear stress. If we reduce that distance, we shorten the distance that stream needs to travel, so it picks up energy there. And by shortening that distance, we also increase the slope. So we have a steeper slope, we have increased velocity, and then as a result, we have more stream bank and stream bed erosion. Here's an example, a case example where, for whatever reason, over to the left side of the stream, looking downstream here, we can see that there was some impacts. Maybe there was a road there or whatever. So folks decided that they were going to straighten that stream. And as usual, they dredged that stream out. They created a berm so that the stream could no longer engage its floodplain. And within a very short time, that stream started to meander back to where it wanted to be. It started to take that straightness out of the stream. It wanted to return to that stable situation. So here we see that point bar that Jeff talked about, recreating a small floodplain side of that meander, and starting to cut into that berm that they left there. And as a result, folks had to go back and do some reconstruction. So to put that meander back again, to reduce some of that velocity, some of that energy, recreate a nice broad point bar that again allowed that stream to put deposition there, and again that vast floodplain, so that stream can engage that floodplain and again drop out energy. So we have a number of videos here that can provide some really dramatic examples. And so this one has to do with stream straightening. So we see here, typical stream, very natural meandering patterns, a bit of migration through the valley. You can see, so that was probably a concern to the landowner for whatever reason in our scenario here. We have a little loss here. Well, the reason these stream table examples are really good is that it's showing water flow as well as bed load movement in here. And so the granular material that they utilized on this stream table is good to reflect. So here you see we straightened the stream out, prevented this meander here from eating into a field or development or structure. And right away, the stream starts to recreate that stable pattern, because that stable pattern evolved over time in a valley that had specific slopes and specific types of materials and all those things that go into the morphological features that help create a stream. So again, you can see that pattern starting to reform, that meandering pattern that we showed right at the beginning of the film. And again, materials being redeposited here. The stream is trying to evolve to that stable situation. But in the meantime, it's redepositing material, it's cutting into banks, it's seeking to create that morphology. And look at all the real estate that's been lost as a result of that. So again, straightening has a lot of consequences that we don't often anticipate. In this example here of dredging, here we are now dealing with those consequences of a destabilized stream. We have a lot of sediment deposited right in here. The stream is unstable. If we left it alone for another 10,000 years, it would be fine. But no, we're going to go in there and we're going to dredge that material. Now, as we dredge that material is now being replaced by wasting banks, by this head cut, where the bed is actually being eroded to fill in that hole that was a result of that dredging situation. And again, the stream is trying to get back to that meandering pattern with a nice stable form, width and depth and access. But here now since we had that head cut and it grabbed material to fill in that hole, we now have that stream being lowered even further from the floodplain. It's disconnected from the floodplain. It's creating more stress on the bank. So we see bank failure up above where we did the dredging operation. So again, we can see the consequences of maybe some of our activities and aren't done in a way that reflects what that stream is looking for. And again, we can see that it's struggling to get back to that pattern, and it'll do this for right through a lot of different storms. And it may happen in a few years, it may happen in 1 year, depending on those precipitation rates. But again, look at the results of that. Now we have another example here where again we have deposition from whatever reason that's starting to create an unstable pattern in here. So we're going to dredge to take the pressure away from this house. Look at the head cut. Again, we have a hole in the stream bed here that's filling in as a result of that stream trying to get back to a stable situation. It's grabbing material from the bed and banks to fill in that floodplain. But guess what? In the time it took to start to restabilize a pattern, it's now eroding over on this side of the bank. So again, we're going to have to go in there and remove that deposition. And we do that again, create a hole, and watch that head cut move upstream. Again, it's grabbing material from the bed to fill that hole. And now this house that probably had no problems for the last 50 years is now ready to fall into the stream because of activity that was done a quarter mile downstream to address a problem there, and they addressed it improperly. And again, as we watch this video run through, again, that stream's grabbing material to fill in the hole and the disturbance that we created. And then upstream, we're seeing the consequences. And boy, I hate to say, but I've life, many, many times. Okay, next we would like to talk a little bit about berms. Now, if you remember, we talked about that importance of floodplains, and when Jeff had mentioned, the critical roles that floodplains play, and I think I reinforced that floodplains actually are a pressure relief valve. So when that water starts to build up and the shear stress involved in that channel starts to increase, floodplains are nature's way of relieving that pressure. So again, they flatten out, they spread out over the vast floodplain and dissipate all of that energy that's in that stream channel. When we start to do things like channelize and put berms, we're actually disconnecting the floodplains from the channel itself. And the result being is that those floodwaters actually start to increase in depth. And as they increase in depth, they also increase in shear stress, and the amount of material that starts to get eroded from the bed and banks itself. So, here's an example where again that floodplain is engaged and it's dissipating that energy in those floodwaters. Here we've actually stacked those floodwaters up, so it's going to increase that shear stress and remove material from the banks, and we're going to get bank erosion, and that erosion and that debris material, that bed load is going to wind up downstream somewhere and actually create new problems. So here's an example. This is what happens constantly is for whatever reason, and you saw this slide earlier when Jeff was looking at deposition. We've had some serious deposition here above this culvert. Now this culvert is probably undersized, or well, it definitely is undersized for that cross section of that stream to carry that flow and that bed load through that crossing in an efficient manner. So when that culvert is full of water, that velocity starts to decrease and we get deposition, we get a lot of that bed load dropping out upstream of the culvert, and as a result we eventually lose capacity in the culvert from what we had. One of the things that is commonly done to maintain those crossings is that folks go in there and they remove some of that bed load, and we all know how expensive it is to truck material. So a lot of times it's placed right along the banks. Well, that does a number of things. There's also folks that, that especially in agricultural operations that don't really want those floodwaters across their crop fields. You have woody debris that drops out. You have, sometimes some real erosion that happens through those fields. And if you have a crop in there, those floodwaters, aren't the best for those crops. But this stream system that we're looking at right here would probably normally engage that floodplain and flow across the road over here and then across that field and into the bigger receiving stream down here where these trees are. And if you look at this, where these two individuals are surveying in here, really that floodplain isn't all that higher than the bed of that stream. So we might be looking at maybe a foot or two difference for that efficient bankful depth for that stream to mobilize and to transport both water and sediment. Well, now we've placed that material in there, and remember what I said previously, that the material that we placed here was material, or is material, that is mobilized during a storm event. So we know that berm isn't going to stay there, especially if we start to pile that water up. And if we start to pile that water up, we're increasing the stress and the energy that's in that system, and it's going to erode that berm a lot quicker. But in the meantime, all that energy and all that water that we've now piled up here is directed right at this stream crossing. And so probably the life of that utility pole and this stream crossing may be short-lived for this world, because again, we've got a berm there that's focusing that water and all that energy towards that crossing. Here's an example of an agricultural operation, and we've got the stream over here to our left, and you can see it's almost the elevation of that field. So that field was functioning as a floodplain, again, to relieve the pressure of that flow through there during storm events. Well, the farmer, didn't want that water out on his field. So he spent a lot of time bringing in material, stacking that material, grading it off, vegetating it, a lot of time and energy to do that. And what happened? That flow came along and it breached that berm, because again, that berm, wasn't engineered with material that's resistant to that stress and that energy that we're seeing in the stream. It breached that berm and entered the field as a concentrated flow. And whenever we think about a berm, that berm will fail. It'll start to head cut through that berm and fail on the downhill side and work its way back. So now we have concentrated flow back into that field, and boy, the damage that was done there is not something that would happen from a little bit of sediment, some woody debris. Now we have concentrated flow that got actually trapped behind that berm and cut through that field. So now we have some significant damage. And one of the things that we commonly run into is that if this berm exists along the whole edge of this field, we might have a situation where we have this flow entering the field, being trapped behind the berm, and it'll go down slope through that valley and outlet further down that valley. And if there's any structures in the way, such as homes or barns or any other structures, it's now refocusing now those flows towards that structure. Again, a very simplistic graphic that we have here. All these little features that we see in the landscape that are hardly ever engaged. They may be dry for 10, 15 years before they're engaged with floodwaters. But over time, and I'm talking about geologic time, over those 10,000 years of evolution for these streams since the last glaciers, all these little wetlands, all these little floodplains, all these little riparian areas that exist in the landscape that we might not think is very significant, really needs to be in place or has evolved in place to be able to adapt to those floodwaters, so that when the flood comes, all those different landscape features are engaged. That water fills those landscape features. Those landscape features store that water until the water goes down, and we have a relatively stable situation. We come in there and we say, well, boy, this hasn't flooded in 25 years, so let's fill that in and do some kind of development in there. And it doesn't take rocket scientists to figure out that when that flood water does come again, we're now forcing that water over into areas that it didn't traditionally flow in. And that might include roadways, it might include homes, it might include all kinds of different infrastructure. So again, we need to be aware of what those long-term consequences are of our actions. The other thing that happens is when a channel is disconnected from its floodplain, as I've mentioned, that velocity and energy in the stream increases because we've stacked the water up, we've concentrated it. I often use the example of think of a garden hose. You have a 1/2-inch garden hose and you turn the water on full blast, and it flows out at maybe a foot or two from the nozzle, and you put that nozzle into the ground and you can actually dig a hole or move material with that nozzle. You put that same flow through a 4-inch drain tile and it just about dribbles out the end of it. So, when you start to play with that configuration of a stream channel, the width and the depth and how wide that floodplain is, you start to play with the energy. So again, you disconnect the floodplain, you increase the energy from the stream, that erosion increases as a result of that. You have damage as a result of that erosion, the flood stage is higher, and all that material that's being mobilized, that's being redistributed, it's going downstream, and it's probably going to wind up in front of that culvert or that stream crossing that we just saw a picture of. Same example here is, for whatever reason, we had some erosion along the road here. And so folks, instead of just filling in the road width, decided to get a little bit more rambunctious. And so what's going to happen to the left side of this stream? So now we've concentrated it, kind of like that mass wasting that Jeff talked about, where it comes down the hillside, it restricts the stream channel, and that stream channel is going to actually increase in velocity. It's got less space. It's like taking that 4-inch drain tile flow and putting it into a 1/2-inch garden hose. Now we've got a lot more force. It's going to go through that section. It's going to rip and tear a little bit more. And, if it doesn't rip and tear in places that we want to, it could be doing significant damage on the other side of that creek. So if we develop on a floodplain, we're with bridges, with bridge approaches, which we commonly do in some of these valleys, with roads, with parking lots. This is all examples. I mean, here's an example, and this is Margaretville in Delaware County along the East Branch of the Delaware River. And make a note of how this is laid out, because I'm going to show some slides right after this that'll show some damage that was done as a result of the storm. But we have the shopping center that's laid out, but we have a nice broad recreational area here, a field, and that's a really good use for a floodplain. Agricultural, recreational uses, all those different things that don't adjust that elevation in that floodplain are really good uses. But again, we have this open floodplain in here. We have now some obstructions or developments in floodplains. When you have that kind of development, you're actually putting all of those structures in jeopardy. So there's more threat to life and property. Again, as I've mentioned, those velocities increase, the energy increases, erosion increases, and again, anything that's in the way is liable to be damaged, and that infrastructure is in jeopardy. And the flood stage downstream is also going to be higher, because again, you've built that water elevation up, and so you have costs and increased flood insurance and even jeopardy to human life. So here's again that same area that has gone through a significant storm. So again, you look upstream, you have these broad floodplains that were able to engage that water, and then here's that recreational area, and here's the development that we had in the floodplain, and here's some close-up pictures of actually that storm as it was occurring, ripping and tearing through that infrastructure. Pretty scary stuff. And when you look at the damage post-flood, you can see that the whole buildings were ripped away. Asphalt was ripped up. When you look at the concrete and the asphalt, you actually got holes that have been scoured right through that what you would think is very resistant material. Concrete, really impressive force that went through there. But look at that park. Now, I'm standing, taking this picture with my back almost against those buildings that were devastated. But here is that recreational area of that floodplain. That water didn't even pull up the grass blades. So in the previous pictures, we saw the concrete and the asphalt ripped and tore. But when we look at a floodplain that's adequately sized, that's broad, that dissipates that energy, we don't even see the grass mobilized. And here's the elevations. There's the floodplain elevation right up here that's being pointed to. That's how high those floodwaters got. But we had a gazebo here that was built to allow those flood flows to go through that area. We have grassed areas that didn't exhibit any kind of erosion at all. And here's those buildings that were devastated back in the foreground. So again, a very impressive example of what those floodwaters do and how functional those floodplains are in handling those energies. Jeff, you got anything to add to that, or?
No, those slides certainly show the definite benefits of having floodplains. And I'm going through one today, believe it or not. We got a snow melt occurring, and I got a guy who lives in a 100-year floodplain, and his backyard has water in it, and they let him build a garage back there. And well, guess what? His garage floor is starting to get a little damp simply because they built it in that floodplain. So it's an obstruction there. Yep. Very, very important. That's for some reason, that's the hardest thing for landowners to understand, is the importance of floodplains and the benefits to having them, for sure.
I know, I always like to tell a little story about, one of the directors on my board that used to farm the floodplains along the Susquehanna River. And all his neighbors grew continuous corn, on those floodplains, and he grew forage on those floodplains. And whenever the spring floods came, all his neighbors would complain that they had lost 1 or 2 inches of topsoil, and he would kind of chuckle to himself and say that he had gained 1 or 2 inches of topsoil on that forage. So how we manage those floodplains, how we provide cover on those floodplains is pretty critical to everyone.
Yes, for sure.